for the opportunity. It's good to see you all here. So I just want to start by saying that if something isn't clear, just let me know. I'd like for as much of this to be understandable as possible. Okay, so what I want to talk about is some joint work with Brent Pym. This is like a series of papers that we're working on, and the first one just went up, I guess in September on the archive. Okay, so the idea is that one can use techniques from Hodge theory and it's like non-commutative geometry to calculate exact results in deformation quantization. As I want to explain, it's generally a really difficult problem to calculate deformation quantizations non-perturbatively. So let me just remind you a bit about what deformation quantization is. Which I'll write as dq forever, because that's way too long. So in classical mechanics, we usually have some symplectic phase space, and the observables in this theory are just functions. So this is, phase space. And then these are just your observables. And typically when you talk about some sort of quantization procedure, what you would like to do is replace this with some Hilbert space. Maybe in this case, you take L2 functions on M, say M's compact. And you'd want to promote each function to some operator on this space. Now, the interesting thing is that, this is a commutative algebra, but we know that if I take, say, just position and momentum, these are going to get mapped to the corresponding quantum operators on the Hilbert space, and we know that these operators don't commute, they commute up to a factor of h bar.
Sorry, in this case, h is move off the base.
Yeah. Wedge dg. Okay, so from one of these tensors, you get this Lie algebra structure. Well, you get this bracket, and then you want this to satisfy Jacobi. So if this has Jacobi, then we say it's a Poisson structure. Okay. So if you have a Poisson structure, which is invertible, then that's the exact same thing as a symplectic structure, where this Jacobi identity for this Lie bracket corresponds to being the symplectic form being closed. So the point is, you can ask given one of these, does there exist some non-commutative deformation of its algebra of functions? So what you want is you want to take functions on your manifold, say now with coefficients in formal power series, and some new product on here. And I want this to be an associative product. I want it to look like, if I take just two ordinary functions, then they should look like, to leading order in H bar, it should just be the usual product. Then at every order in H bar, I'm going to have some bi-differential operator applied. These things, these BI are bi-differential. Okay. So this is what it should look like. It should be associative. And I want to be able to recover the Poisson structure from it. So if I take F star G and I subtract this from G star F, well, these have the same 0th order term, but if I look at the linear term in H bar, let H bar go to 0, this should recover the Poisson bracket of these two functions. No, it's like these are differential operators, and like in both slots on F and G. So think of it as like a tensor product of two differential operators. Okay. So this is what I'll mean by a deformation quantization. If someone hands you a Poisson manifold and you're able to produce one of these deformations of the algebra of functions on the manifold, satisfying these conditions, then you win. So that's the goal. And this is a really hard problem to do because you either need to prove that this exists all the time. So I should say, if you have one of these, then like we've just seen, you can recover the Poisson structure from this. It's easy to go from one of these, like H bar families of algebras, to recover the Poisson bracket. But the hard part is going the other way. So the solution to this was figured out by Kontsevich in 1997. The year I was born. I wonder if it occurred to him the moment I came into this world or not. But he proved that every Poisson manifold admits I'm going to say unique or canonical deformation quantization. So you can always find this. And moreover, he gives a formula. Which is pretty incredible. He actually just writes down the function. It's yeah, that's what he does. So he solved the problem by just not proving like it abstractly exists. He just calculated what it has to be for every Poisson manifold. And I can write it down for you, sort of, not fully. So it's going to be a full formal power series. So I'm going to sum all powers of H bar, and the nth order in H bar, there's a collection of graphs, which I'll call Gn. And I'll just sketch a couple of these. But for each one of these graphs, you're going to associate some bi-differential operator to the graph, which knows about the Poisson structure. And you're also going to assign some complex number in front of it, which is a weight. So yeah, this is a bi-differential operator, which depends on a bunch of graphs. This is a complicated weight that you get by taking integrals of differential forms over configuration spaces of points in the upper half plane. So a typical graph might look something like, here's F, here's G. I can do something like this. Well, let's just stick with the simplest one. This graph here essentially corresponds to the leading order term. But they're just, yeah, a bunch of graphs which look like this. I don't really want to talk about the graphs today. They don't matter so much. But the point is that this is your solution. Well, not your solution, Kontsevich's solution to this problem. And to actually calculate this thing, you're going to need to take a sum over an infinite number of graphs. And for each one of those graphs, you're going to have to calculate some integral over configuration space. And that's going to take a while. So there are a few questions. Sorry?
Gamma is it?
Gamma is an element of Gn. This is some set of what you might call Kontsevich graphs. Yeah. I should also mention he proves a stronger statement, which is some L infinity quasi-isomorphism of two DGLAs associated to this, for which this is just a corollary. These graphs are some special case of that. But okay, regardless, here's a formula, and we have some questions. First question is, does it converge? Another question would be, what does it converge to? If not, could we do some resummation or something like this? And then there's one other more subtle thing, which is dependence on a certain choice you have to make, which is called an associator. So this is a gadget which is going to give you, if you make different choices of associators, I don't want to say what they are. I don't fully understand what they are. But different choices of associators are going to give you different weights. So these weights in the formula actually depend on this auxiliary choice. And in Kontsevich's original paper, he used the weights that you would use if you were just calculating from like math 136, just like standard method of integrating, but there are other ways of integrating that they don't teach you in Calc 2. Okay, so answers to these, there's almost no general results. I would say most of the cases we actually understand this formula are actually in Kontsevich's original paper from 1997. So there are other contexts for deformation quantization where there's other results like C star algebras, but that's not what I want to talk about. Okay, so let me just do an example. Let's take M to be this non-compact 2 torus and pi to be this torus invariant Poisson structure. All right. This is a nice bivector. You can check using like certain equivariance properties of Kontsevich's formula that the star product in this case has to look like the following. So x star y is going to be some formal power series times xy, and y star x is going to be the same formal power series, but in minus h bar, again, times xy. Again, when I write star here, I do mean I'm calculating with this formula. Yep. Basically, it's GLN equivariant, and so when you look at the possible weights, of the monomials that could come out here, it has to be something like this. Okay, but regardless, this means that if you look at this, this means that the star product is determined up to isomorphism by this parameter. Let's call it Q of H bar, which is W of H bar over W of minus H bar. Then the algebra looks like so the algebra is then this quantum torus type thing. It's going to look like C on X and Y with H bars, where X times Y is Q of H bar Y times X. Okay. So Kontsevich's algebra that he produces is isomorphic to this non-commutative torus. Say holomorphic. Some non-compact holomorphic Poisson variety. Or algebraic. Either's fine.
You're telling me what the star product is on generator.
That's enough. All right, it's a CH bar linear. Yeah. Okay, so that means to compute this, you need to compute Q of H bar, or you can compute Q of, or W of H bar. And many, I don't know, a few years ago, Brent worked, well, he with some collaborators wrote some software which actually computes Kontsevich's formula explicitly. And yep. Oh. Well, what would you call it if there were no H bars and this wasn't there? Oh, sorry, these should be plus or minus. Yeah, non-commutative affine space was just on the board. This is non-commutative torus. Yeah, thanks.
This basic clarification.
Yeah.
If I wanted to compute E to the X star Y, can I do that?
E to the X? No, I mean, this is some like flat family of algebras over H bar, which means that it's going to have the same generators regardless. So I mean, you only need to know what X star Y is and Y star X is.
I should be able to compute this on any logarithmic function on C or squared, right? Just do it from power series, term by term.
Yeah.
But they have the power series. Because we call that a CH bar linear, but I don't.
Well, just E to the X is like, right, as 1 plus X squared over 2, and then just you apply it to every one of those terms. Yeah.
Is that extra variable or
Nope.
that's applicable?
No, that's fine.
Sorry.
Yeah. Yeah, if you want, think algebraically. I certainly do. Okay. But when we compute this W of H bar, we get the following. Sorry for writing actual numbers. Okay, so at order 4, it's this. This maybe you could do by hand if you were dedicated. Probably wouldn't want to. Okay, and then you'll get to order 6. And working by hand, you'll find that the next term is 251 over 2048. The Riemann zeta function of 3 squared over pi to the 6 minus some other rational number. So the point is, once you get to order 6, you see conjecturally transcendental numbers appearing in Kontsevich's formula. In general, all of the terms are going to be these things called multiple zeta values. So the point being, you would never do this by hand. And it's basically impossible, even for these simple Poisson structures, to actually calculate Kontsevich's formula to all orders. But something remarkable happens when you calculate Q. Remember, this was W of H bar over W minus H bar. It looks like this. And then you can only go up to order 6 on the computer. To get this term at order 6, it involves like 50,000 plus graphs. And for each one of those, you have to do configuration space integrals. It's a mess. But when you calculate this, you just get what looks like the exponential function. So one would probably guess at this point that Kontsevich's quantization, or rather, let me say, if you have x, y, let's say your Poisson structure is not just xy, del x wedge del y, but if I put some lambda here, then you might guess that under deformation quantization, you get this non-commutative torus algebra. This Q of H bar should be e to the lambda H bar. Okay. So over here, I was taking lambda to be 1, but this is what you might guess. Yeah. Yeah. So for each choice of this thing called an associator, this W is going to be uniquely determined. But actually, if you choose different associators, these numbers are going to be totally different. These W's that you see actually depend on the associator. But for every choice of associator, this Q, this ratio of them, is actually the same. Oh, it's completely the same thing. So in that case, you're going to have your Poisson structure is going to look like lambda ij, xi, xj, del xi, which del xj. And then you're going to get, you'll hypothesize that, I keep forgetting plus and minus. It should look like this thing here, same as before. But xi, xj should be qij of h bar, xj, xi, and you would guess that qij was just e to the lambda ij h bar. Sorry, does that make sense? Okay. Yeah.
The thing was unique. And there's not much to do. Just take the classical what you wrote down and check.
I guess maybe unique is the wrong word. Maybe I should have said canonical. Like there's a canonical quantization.
This is a quantization.
Yeah.
But there's not much to that.
Yeah, definitely. But I guess the thing is to see that this is actually what Kontsevich's formula produces is the difficult thing. Yeah. And seemingly different choices of associator should a priori maybe give you different algebras, but here it seems like they're not. So there's this question of, does your quantization depend on this choice of associator? And it looks like in this case it doesn't. And hopefully we'll see that. Yeah. Poisson cohomology of these? Like what are the actual Poisson cohomology groups of this Poisson? Yeah. So these aren't necessarily symplectic.
No, the general one is the Torus one.
Right, for just XY. Yeah. That's right. Yeah, I calculated it. Yeah, it's just going to look like an exterior algebra on the Lie algebra. Think of the torus. No, read my thesis and you can see the calculation in there. It's like you reduce it to the G equivariant. Like there's a torus action on everything, and you have you can just restrict almost always to the torus invariant chains or cochains. And those you can just calculate what they are, and they're going to look like the exterior algebra and the Lie algebra. Yeah. Okay. Any other questions? Okay. Let's see how to prove this. So we have a guess for what this is. And Kontsevich had this brilliant idea that instead of actually calculating using the formula, you can interpret this as a problem of like comparison of parameters. So over here, there's some moduli space of Poisson structures. And maybe here's the Poisson structure you're at. And you want to think that in some formal neighborhood of this point, there's some, this is what I believe the moduli space of associative algebras to look like. I think it's terrible for some reason. I have no reason to believe this. Someone correct me if I'm wrong. But basically around this point, this straight line is going to be sent to some maybe more complicated shape in the space of associative algebras. Okay, so Kontsevich's formula is really giving you a recipe for taking a formal neighborhood point here to a formal neighborhood of a point here. And what you could instead do is maybe for nice Poisson structures, like here we see that there's a parameter, lambda, or here there's a whole matrix, lambda ij, and over here there's a whole matrix of parameters, which are these qij's. So maybe instead of actually just like trying to calculate what the qij's are, you could factor this map. Yep.
What was the?
This is, oh, sorry, I just wrote an H bar. Let me write Kontsevich. So that formula I wrote down before, it's taking a Poisson structure or any formal Poisson structure on your space, and it's producing for you a an associative algebra from that.
There's sort of moment around wait to say where this.
No, he wrote a formula, and it's yeah, this is sort of just like a conceptual thing, more or less. Although in certain examples, like maybe we'll talk about it today, you can be precise about what the moduli of Poisson structures on a particular space are and what sort of algebras they have to go to. But yeah, maybe the idea is then that you can factor this map through some auxiliary space of, say, Hodge structures. And that would be nice. Like, for instance, over here, you would hope that maybe you could associate some Hodge structure to your Poisson variety. And if you had some like family of non-commutative algebras, you could associate some Hodge structure to those, and they would have parameters. What do Hodge structures do? They calculate parameters associated to geometric objects, like the tau parameter of a torus, stuff like this, right? And here we have parameters. Okay, so this would be great and all. But then what you'd really hope for is some sort of isomorphism here if you restricted to an appropriate class of non-commutative algebras, for example, quantum tori, like this. And if this was an isomorphism, you could call this a Trelli theorem. And if this diagram commuted, then instead of doing this and calculating infinitely many graphs, you could, well, calculate some Hodge theoretic data here, calculate some Hodge theoretic data here. And if you knew that these algebras actually came from the quantization, then maybe you could, just follow the triangle in the other way. Okay. So I'm just proposing a factorization of Kontsevich's morphism. Yeah, I mean, that's what I'll be thinking of. I'm only going to want to vary the Poisson structure. Okay. So to do this, the first thing you'd have to do is associate Hodge structures to a Poisson variety and associative algebra. Right. So I'll talk in detail about the Poisson case. The associative case I know how to do for tori. In general, still working on it, but let me start talking about log Poisson manifolds. Okay. So before I get into the actual geometry, are there any questions about the setup or the strategy or anything like this? Make sense? Something's hard to compute. Maybe we can do it easier if we do it this other way. Okay. So, all right. So definition. So I'm going to say, also now I'm working completely holomorphically. There are no more real manifolds. Well, not just C infinity, but anyways, a log manifold, I'm going to say, is a pair X. So this is the log manifold. It consists of two things. The first thing, this is a compact Kähler manifold. And this boundary of X is a normal crossing divisor. Okay, it's called the boundary. And I'm going to denote by X naught this compact thing minus the boundary. This is the interior. Okay. And I want to think of this interior as being the primary geometric object. So, for instance, if you have a morphism of log manifolds from like X to Y, which restricts to an isomorphism on the interior, then I want to think of that as being an equivalence. Okay. In other words, different compactifications shouldn't matter as long as there's a map between them. All right, so from this data, I can produce this logarithmic tangent sheaf. So the notation here is bold, maybe. I'm just writing X, but by X, I mean X is a log manifold. So I mean this pair. So I'm going to let this denote the tangent sheaf on the compact object, which has which is tangent. So these are things which are tangent to the boundary divisor. Okay. So these are vector fields on the compact thing, which are, this is P2, and these are the coordinate hyperplanes. Then they're like vector fields, which are always going to be tangent to these boundary divisors. Yes. Yeah, all of these are holomorphic sheaves. Okay. So from this, I can produce the logarithmic polyvector fields, which is just the exterior power of this, and the forms, the logarithmic forms. Well, the logarithmic one forms, these are going to be the holomorphic one forms on the boundary, which can have order one poles along the boundary. Okay. And okay. So these are basic objects of log geometry. And I'm going to write the theorem cohomology of this log variety. It's just going to be the cohomology of this complex of logarithmic forms. Okay. And as Deline tells us, this is actually just isomorphic to the theorem cohomology of the interior. All right. So this is, if you haven't seen this before, this is incredible. But right, I'm saying the log forms on the compact thing, their theorem complex computes the theorem cohomology of the interior. Okay. So with this, we can say a log Poisson structure on this log manifold. So what is this? This is a Poisson structure in the normal sense. So like a holomorphic Poisson structure. So I'm going to swap to sigma instead of pi. So it's a global section of wedge 2 of this holomorphic logarithmic tangent sheaf. So it is a Poisson structure. So in particular, it's like it satisfies the Jacobi identity, but also I want that the boundary divisor is a Poisson subvariety. Okay. So the functions vanishing on here form like a Poisson ideal. Okay, any questions about that? Yeah. What resolution? Bott-Samuelson. I don't know what that is. We should talk though afterwards, and maybe I can find out. I'll give you an example right now though. So for example, we can take x to be Pn and the divisor to be the union of the coordinate hyperplanes. Right, so if it were P2, it'd be like, this is P2, here's, so naught is 0, 1 is 0. Okay. And in this case, the interior is just going to be C star to the n. And I can take a lot of things for Poisson structure, but I'm going to take what I wrote before. So lambda ij, this is some holomorphic function. I was using Z. Okay. And I want to take this to be my Poisson structure. So you can see it is invariant. Like if the space of polyvector fields has a natural torus action on it. And if you are invariant under that torus action, you're going to be able to extend to the entire projective space. So these have degree -1, these have degree 1. The whole thing is going to have degree 0. Sorry, these are just numbers, not holomorphic functions. So this Poisson structure will extend to all of Pn. Okay. If you want to just see what the Poisson bracket is, this is just saying that Zi with Zj is lambda ij.
Poisson subvariety of X, where the Poisson subvariety comes from the Kähler.
No. Very important. Thank you. The Kähler structure does not matter to me whatsoever. The fact that it is a Kähler manifold and therefore has like a symplectic form on it, I don't consider that symplectic form at all. That does not exist. There's an auxiliary holomorphic Poisson structure. So some holomorphic section of this sheaf. And, you know, so this gives OX, like I now have a Lie bracket. So sigma is going to give me some Lie bracket from OX, like times OX to OX. And it's going to turn this into a sheaf of Lie algebras. And I want this to be true where this is the ideal sheaf. For the boundary. Okay.
That's what there's OS.
Oh, sorry, this is OX bar. Yeah. So.
Oh.
Yeah.
So did you use the scalar for something else?
Never. The Kähler structure, other than for like having like hard Lefschetz theorem maybe, or something like this, will never come into play. Yes. I care that a certain spectral sequence degenerates. That's all. Okay, cool. So one word of warning. One of the nice things about like, well, what Deline proved that, so using resolution of singularities, you can always find compactifications of Poisson, or not of Poisson varieties, of algebraic varieties, which will look like this. They'll have normal crossing boundaries. This isn't true in the Poisson case. The issue is that Poisson structures, like when you resolve singularities, you blow up a bunch of things. But Poisson structures don't always lift to blow-ups. So it's actually a really difficult question whether you can always find, you know, given one of these interior things, can you always find a compactification of it in this way? So in particular, there's easy counterexamples where you cannot do that. Okay. Any questions about log Poisson structures? Yeah. I'm ashamed about how little geometric representation theory I know. I don't know what the Poisson structure on the Flag variety looks like. Yeah, we can talk about it after. Yeah. So I mean, this is the main example I want to think about today. Okay. So let's see. It is 3. Do we stop now or in 10 minutes? Up to me. Let me give an example of something that doesn't work, and then we can stop. Okay, so something where this doesn't work is if I have Y, a K3 surface, and this is its holomorphic symplectic form. And let this be some closed positive codimension subvariety. Okay, so I'm going to view this as a holomorphic Poisson structure by just inverting this holomorphic symplectic structure. So this is clearly a Poisson subvariety. Right, I mean, it's a symplectic subvariety because I can just restrict the 2 form to this open complement. But Z is not, just for dimension reasons. Right, it's 2 complex dimensions. It's not going to. Positive codimension means it can't support a holomorphic symplectic structure. So imagine that this is the thing that we started with, and we want to find some Poisson compactification of it, right? Like nothing. We'd want this to be like a a Poisson subvariety. So if we were trying to compactify this to y using this as the boundary divisor, we need this to be normal crossings. But if that were the case, this would never be a Poisson subvariety. Yeah. Because I mean, we'd want it to be a symplectic subvariety, but it's positive codimension, so it can't support a holomorphic symplectic form because it's not big enough. Okay, but maybe we could compactify this in other ways, but this is minimal, so the only way that we can actually do this is by compactifying to y and then blowing up a bunch of points. So basically, the only way we can compactify this, we want y minus z bar. This is going to be y plus a bunch of blowups. And these blowups, the exceptional divisors won't be Poisson, and this z that we add back in isn't going to be Poisson. So none of the possible compactifications of this thing are going to make the boundary divisor a Poisson ideal, or a Poisson subvariety. So that's okay. There are a lot of cases where you can actually do this. And I guess maybe now we'll break for 10 minutes. Any positive codimension one, yeah, because it would it'll be a symplectic subvariety if it's Poisson in this case, and there's not going to be any of those. Or actually, what are the points? Or at least I think they'll have to be even dimensional because a point actually the thing something the point.
I'm confused. The condition you wrote on the divisor,
Yeah,
that looked to be like quasi-tropic.
that might have been twice. I guess I want the Poisson structure to restrict to a Poisson structure on the subvariety. For it to be a Poisson subvariety.
So just like when you take a residue or something, like what's the matter?
Oh, okay, no, sorry. Poisson subvariety is one where it's a Poisson and zero. So you want that,
So I comma A is an I.
yeah.
Yeah. Right.
Yeah. So,
Okay, great.
yeah, sorry about that.
Can you talk about restricting the Poisson structure because it's tangent, it's wedged to.
Yeah, I mean that would be like taking residue.
No, because there's poles, there's like poles, the way this is built in, there are poles at the boundary. So what do you mean? Yeah.
Well, no,
It's
the
a
vector fields
section,
are
the vector
tangent.
field section of wedge two of the like TX bar.
Yeah, the logarithmic.
Maybe I'm not
This is
understanding.
TX minus log del X.
Yes,
This is saying that these are tangents to the divisors, so you can just restrict them.
Sorry, yes, okay.
Yeah, so if you're working with
Yeah,
these,
okay, yeah.
then you're gonna have to take residues.
Okay,
Yeah.
right, thanks.
Yeah. You're gonna ask me about stacks. I would like to know these examples.
So I think so. In a sense, this
Uh-huh.
we are thinking about this Poisson structure is a wrong way.
Okay.
Don't do blow up. There's an abundant supply of such Poisson structures coming from cluster algebra.
Okay.
Classes with Poisson compatible cluster structures.
Okay.
Because they are
They
the
finally got.
Interesting.
very strong with a Poisson variety on which you have the canonical Poisson structure.
So I finally put a.
Usually so your X zero, usually it's a Torus orbit or something like that.
Okay. Okay, yeah, definitely, please. Okay, are there any questions? Residual questions before we get started? That's fine. I understand. Okay, yeah, so addendum, this is what it means to be a Poisson subvariety. It should be like a the algebra ideal. Okay, so what I want to do is actually talk about the Hodge theory. So let me just remind you that, well, Hodge structure is something which looks like the cohomology of a compact Kähler manifold. In particular, you have a lattice, you have conjugation, and you have this PQ direct sum decomposition. But another way of thinking about it is some complex vector space together with some lattice. Let me call this V Durham, V Betty. This here is an abelian group. We've got some map from the complexification of this abelian group. We call this map C, comparison, V Betty to V Durham. And then I've got a decreasing filtration, say Hodge filtration on V Durham. And I've got an increasing weight filtration on V Betty tensor Q. Okay. So I'll explain where all of these things come from in our context, but this is what you would call a Z mixed Hodge structure. Well, this is the data that goes into it. You need to check that certain quotients with respect to the weight filtration give you pure mixed Hodge structures, but let's just try to get this data first. Okay, so let's do it. From this X sigma, I'm going to define a double complex of holomorphic sheaves. So it's going to be these logarithmic differential forms together with the Durham differential and what I'm going to call delta sigma. So this delta sigma, this is the operator, which is the difference of d I sigma and I sigma d, like in the Cartan calculus. Okay, where again I sigma here, this maps my k forms to k minus 2 forms just by contracting with the Poisson bivector. Okay, you can check this is a double complex. The fact that this squares to 0 is equivalent to the Jacobi identity. And I'm going to define the Poisson homology of X sigma to be the cohomology of this complex. Okay. So if you want, you form the total complex, you take a Dalbo resolution of everything, take C infinity global sections and compute away. Okay. Now, yeah, so it's the Poisson homology. And this is great. Maybe this is some new invariant associated to these manifolds, but I have this map I sigma, which I wrote down. some endomorphism of the differential forms, and I can exponentiate it to get some automorphism of the differential forms. So this, if I view it as a map from this double complex to just the usual theorem complex, this is an isomorphism of complexes, or of bicomplexes. That's to say that what I want, E, the I sigma, D, E to the minus I sigma, this is going to be D plus delta sigma. Okay. So it looks like we have achieved nothing and should go back to the drawing board. It looks like this is the same thing as the theorem cohomology of X. And this is true, they are isomorphic. But one important fact is that on the logarithmic differential forms, there's a certain filtration that I want to consider. Okay, so is this clear to everyone? Are there any questions about this? Okay. X is the log manifold. Everything here is logarithmic forms. Yeah. In particular, this contraction operation preserves the logarithmic subcomplex. Yeah. Okay. So let me just consider the even theorem cohomology of X. And what I'm going to do is I'm going to take the Hodge diamond and I'm going to give it some decreasing filtration. So I'm going to put F0 here. I'm going to put F minus n here and Fn over here. And I'm just going to cut it up into columns like this. Okay, this is different from the usual Hodge filtration that you've probably seen in like Griffiths and Harris. Okay, so I just want to make sure I get this wrong every time. Increasing, it should be a decreasing filtration. So if this is Fn, then I want this to be Fn minus 1. This is the whole thing, and these are the little pieces for what I care about. Okay, so I start here. Maybe in this it looks like an increasing filtration. I don't want to think about it right now. Okay, so I'm going to start here, and let me just say that I'm a surface. So here I'll have omega 2, 0. And this will be contained inside of this plus omega 2, 2, omega 1, 1, and omega 0, 0. And then that's, at the end, I'll add this in. So there's a 3-step filtration here. Okay. This is what I'm going to call, so this inside of this, inside of this. I'm going to call this the usual Hodge filtration, and I'll just write it like F upper bullet. Okay. So this is Hodge filter. So this is the natural filtration that you get if you view the complex manifold as a generalized complex manifold. It's also the sort of natural filtration that comes from non-commutative geometry, and like a Hochschild homology has this type of filtration on it. And with this filtration, we see that this operation, this one, does not preserve the filtration. Right? It's going to take, like, so if this is the smallest piece of the original filtration, then it's going to map it down to a mixed degree form in all of these things. Okay, so like on the surface, I'm going to take e to the I sigma, apply it to my original filtration, and I'll call this new filtration F sub sigma. And on the surface, it'll look like this. In lowest degree, I'm going to have 2 0 forms. And here I'll have sigma applied to, or contraction of sigma with 2 zero forms. So everything which looks like a thing here and then its contraction down here. This will be contained inside of here. These aren't going to be affected at all by this change, but these ones are going to be. Okay. And then the last one is, all even things. Okay. Is it clear how the filtration is changing? I'm just like taking these vertical columns, and when I apply the bivector to them, I'm going to drag a 2 zero form to write e to the I sigma. This is like 1 plus I sigma plus I sigma squared over 2, etc. So it's going to take a form here, and it's going to send it to that form plus the function I get by contracting the bivector into that 2 form. Okay. Here's a new filtration. And the wonderful thing about the original Hodge filtration that I'm erasing is that it gives you a spectral sequence, and that spectral sequence degenerates at the second page, and that's what gives us the Hodge structure on the cohomology ring of the compact Kähler manifold. So the theorem is that the spectral sequence associated to this filtration also degenerates. At, I think it's E2. In other words, like in particular, the theorem cohomology of X inherits the filtration. Okay, so theorem cohomology, the complex structure and Kähler structure gives you a filtration on here. And what this is saying is that if you have a holomorphic Poisson structure, one of these logarithmic holomorphic Poisson structures, then you can deform that Hodge filtration like using this Poisson structure. Okay. In particular, like since the dimensions of all of the things aren't going to change, you can think that there's a map from like Poisson structures into flags in the cohomology of X. But yeah, okay. Any questions about this? Okay, let me just give a concrete example. So example. So on C star to the n, which I'm thinking of as En minus the hyperplanes. Advisor. The theorem cohomology. Well, yeah. This looks like the exterior algebra on my coordinates, Z1. So here it's something funny kind of happens, which is that the ordinary theorem cohomology of this is actually generated by logarithmic forms. Right? These forms are like the obvious generators of this cohomology, and they are actually the ones which come from the logarithmic complex, like according to Deline. So it's sort of a very nice situation. So now in this case, the top degree forms, it's like H, N, I guess, the thing in the far left of the Hodge diamond. So this would be one of the parts of the original like vertical Hodge filtration. But in the new Hodge filtration, it's going to, this new leftmost piece is going to look like e to the I sigma applied to this. just applied to this generator. Okay, so this generated, like in the Hodge diamond, it generated this leftmost part here, right? This differential form, it's of like degree, it's an N0 form, it's going to generate this, and that was one of the original parts of the Hodge filtration. But now what's going to happen is inside of this theorem cohomology, I'm going to get a new line spanned by this generator, but it's not just inside of here. It's entirely, it's going to be in all of these even degrees. And I'll just get it by contracting this with the bivector a bunch of times. Okay. So, yeah. Okay. Is the Hodge filtration somewhat clear? Yeah. No, so to this top form, here's yeah. Sigma is it's log canonical. Yeah, sorry, here's sigma. Let's just take it to be like lambda ij, zi, zj, del I, wedge del j again. So in this case, the new like leftmost part of the deformed Hodge filtration is going to be spanned by the class represented by the line, which is the following element in even theorem cohomology. Okay. So I'm going to write down an element of theorem cohomology. It's of different degrees, and it generates this new like leftmost piece of the Hodge filtration. So it'll be this, and then also the contraction of sigma into this. So that'll be like, I mean, I don't want to write out what that will be. But if I contract this bivector into this, then I'll get an n-2 form, right? And then if I keep contracting, you get an n-4 form. And I keep doing this until it vanishes. And that is a single differential form of mixed degree. And that is the new leftmost generator in this Hodge filtration, okay? So the point is that this new filtration remembers the Poisson structure, okay? All right. Great. So let me just also say there is a weight filtration. So the usual weight filtration works. Okay. And let me tell you what this is. But I'm just saying that you don't have to change the weight filtration to accommodate the Poisson structure at all. So here, the weight K part of, so I'll put the degree at chain level, or the filtration at chain level. So on K forms, or that's doubling up on K. How do I want to write this? Okay, so I want to define for you what the weight filtration is on differential forms. So you need to remember that these are log forms. Okay, so this is going to be things which have at most, sorry, do I want at most or at least? Yeah, so this is going to be omega k x wedge omega dot minus k x bar. Okay, so these are, sorry, I think, no, this is right. Okay, so these are the log forms. And remember that log forms don't have to have poles, right? They're allowed to have things like dzi over zi in them, but you know, dzi is also perfectly fine. And this, okay, so this is saying that these are things which have at most k poles. Because these are the things which are holomorphic. These can be meromorphic with poles on the boundary. Yes, so this is a lattice. Yeah, so what do I want to say? So this is defined at the level of the complex vector space. It'll induce a filtration on the cohomology, and that's complex. And then Deligne proves that it descends to a filtration over the rational numbers. Yeah, so that yeah. Okay.
Things in the thinking, hey, general will have a direction.
Yes, that's true.
Like omega less than KD or something, otherwise this isn't increasing, like if you take K to be N, this has to be N folds.
No, because if this is K plus 1, then I'm allowed to have K plus 1 poles.
Yeah, but I'm saying that like
Oh, sure. I mean, there's like it's like a piecewise defined function. If it's above a certain bound and it doesn't make sense, then it's just the whole thing. Let me just put like
is this filtration on? Oh, okay.
Yeah, sure, like this. Yeah. Okay. So the point is this induces a weight filtration on the Durham cohomology of X. And now at this point, we've got our complex vector space, which is the Durham cohomology. We've got a filtration on it, and we've got another filtration on it. So at this point, we have this, our Hodge filtration and a weight filtration. But there's something missing from this, which was a lattice. So remember that on like a compact Kähler manifold, the cohomology has like the singular cohomology as a lattice inside of it. And here that's also true. We could use the singular cohomology. So we want to find a lattice. And there's a couple options. The first thing we could do is take like, you know, the even cohomology. So again, let me just, it's fine. We could just take the even / odd cohomology groups living inside of here. And, you know, same for the odd. This is what you would do. This is the first thing you would probably do. Maybe something a bit better would be taking the Chern character from the 0th topological K theory into here. The reason this is a bit better is because it's sort of, it does play a lot nicer with the weight filtration in the sense that really I'm lying to you, and there should be something here called a Tate twist. And the Chern character naturally incorporates these Tate twists when you take like curvatures of connections. So this works a bit better. But we could do something seemingly crazy where we define this invariant polynomial here. And this is a symmetric polynomial, and it's going to determine some characteristic class. Which is, say, like this thing evaluated on the tangent bundle, like in a sense of Chern-Bay theory. And then we could take its square root. So this is some polynomial in, or like, yeah, polynomial in terms of Chern classes of the manifold, and you could ask to take its square root. You'll get some cohomology class. So ultimately, there's this. It's the Tom class up to e to the minus c1 of x. Yeah. Yeah, Todd class. Yeah, yeah.
Square root
Yeah, so this function has a square root.
of the help.
Yeah, sorry. Yeah. Sorry. Square root of this. Thank you. Yeah. So this is like the square root of what's called the a hat class. It looks like 1 minus 1 over 48 times the second Chern class of x and a bunch of other terms. It lives in the even theorem cohomology of x. Okay. So this is, you won't believe me, but this is the best choice. The reason it is the best choice is because when you do quantization, when you look at Kontsevich's morphism, really it should be interpreted as what he did as a map from the polyvector fields on your manifold. So I said something about Poisson structures, right? So that was wedge 2 of Tx. But really, you can take all the polyvectors, and there's a map from this, which has additional structures, into the Hochschild cochains of the quantized algebra, or, well, of OX. You get 2. If you don't take the square root, you'll just get a 2 where?
The Chern K0.
Oh, I'm sorry. Yeah, so basically you can also do this because it's more compatible with Herzberg-Riemann-Roch and Poincare duality. Yeah. So sorry, I never actually said what this map was. So the map we'll call it CX. This is going to be, I'm going to do the Chern character, and then I'm going to cup with this characteristic class. So this is now a map from K theory of X into the even theorem cohomology of X. And this is what I'm going to take. It's called the charge lattice. Okay. So the reason it's called this is because it corresponds to certain charges of like d-branes in string theory. And there's these papers where they're calculating like things involving d-branes, and from those like correlation functions and stuff, they just like deduce Riemann-Roch, basically, which I thought was very cool. Okay, so we have this strange lattice sitting inside of the theorem cohomology, and then the theorem is then that if I take this with the weight filtration, the Hodge filtration, and this charge lattice, that this is a mixed Hodge structure. And I'll denote it K0 X sigma. Really, from what I've said, this should be like H even, and these make sense. So the even and the odd cohomologies are each going to be their own separate mixed Hodge structure in this story. So options 1 and 2 are the same rationally by Attia Herzebrook's paper. And then this, I mean, cupping with this is invertible. So it's sort of just like a nice, more, I mean, so it is a different lattice. You get different classes. Yeah. Yeah, so they are different.
Also the same.
Rationally. Yeah. That's true. So it's like a rational automorphism of the cohomology. So they're isomorphic lattices. Okay. Cool. So in the last little bit, let me just say how we actually get parameters, right? remember the whole goal was to take a Poisson variety and calculate its deformation quantization. And to do this, we said that, okay, instead of actually calculating this formula, there's parameters in this thing. Let's calculate these parameters. So I'm going to show you, or just sketch, how you do this for just like the two torus. Let's take this, compactified to P2, and let's let sigma be this bivector. So from this, if we compactify using P2, then I'm going to get this mixed Hodge structure, okay? The one I just sketched for you how to create. From this, I have a mixed Hodge structure. And what I can do is I can look at the weight filtration. So I'm going to take the weight 0 part of this. This is just Z, okay? This is going to map into the weight 2 part of this. And then the quotient, so I was really brief about what the weight filtration is, but this is going to like consist of things which have degree 2 poles. Okay, so the quotient is actually Z, but there's this thing called a Tate twist here. Let's not worry about what it is. It just means that there's a factor of 1 over 2 pi I. And then it's going to be generated by this class, which is dz1 wedge dz2 over z1 z2 minus lambda. Okay. So here's so this is a mixed Hodge structure, and the weight filtration is actually a filtration by mixed Hodge substructures. So this right here is a extension of this by Z in the category that this is actually just isomorphic to C. Sorry, is it C? Oh, it's C star. Yeah. Okay. And when you calculate what this is, I mean, so the way that you do this just really quickly is you split this as abelian groups, and then you see, okay, I can split the weight filtration as abelian groups, but these also have residual Hodge filtrations on them. So then you need to keep track of when I split it, how does this fail to respect the Hodge filtration? And from that, you can actually produce an element of C star. Okay, but the point is when you do this, this exact sequence, or this extension, gets mapped to the number e to the lambda. Okay, which is somewhat believable because it's there. Yeah. Okay. So and more generally, if we had like a whole, not just a two torus, in general, the whole Poisson structure would get mapped to e to the matrix, which is e to the lambda ij. Okay, so you just take like the matrix exponential of the coefficients of the Poisson structure. Or not matrix exponential. I don't know if there's a word for it when you exponentiate each entry of the matrix individually. If you know, let me know. Okay, and this is also interesting because this means that the mixed Hodge structure determines this Poisson structure up to 2 pi I shifts. Right? If I could take a logarithm, then I would know the Poisson structure. Okay, in the last 7 minutes, I'm going to say how well, 7 minutes before questions. Okay, I have a bit more time. So in the last few minutes, I want to say how we do this on the non-commutative side. So if you remember that picture that I drew before, we had the Poisson moduli space, and then there was like the Hodge moduli. And then here there was like associative algebras. So the thing is, we believe that the quantization of this is some non-commutative torus, right? So I want to take some non-commutative torus algebra. I'm not going to work formally anymore. There's no need. I mean, you could, but let's just take something like this, and I'll call it AQ. Okay. So the first goal is to associate some mixed Hodge structure to this. Okay, so we want an MHS. And actually, maybe we want better than that. Maybe if this is the Q plane, which looks like C star, then over each point, so if this is Q equals 1, I'm going to have, you know, O of C star squared. It'll be commutative. But over another point, you know, this will be non-commutative. In general, every fiber other than Q equals 1 is going to be some non-commutative algebra. Okay. And maybe what I want isn't just a mixed Hodge structure, but I'm going to want some variation of mixed Hodge structures over this C star in terms of the Q coordinate. Okay. So that's, I mean, I'm not going to say that's what we'll do because we don't have time for that, but that's what you do. And basically, here's how it's done. There's a sort of dictionary, if you want, where if, okay, I mean, I don't even really need, well, let's say I have one of these log Poisson varieties, and here I just have some associative algebra. Okay. You can ask, how do I translate the things that I had before into non-commutative algebras? This seems difficult. Well, there are invariants that are cooked for this. So you want to replace the theorem, the even/odd theorem homology by this thing called the periodic cyclic homology. In particular, if this is functions on X, then this is H theorem. Okay, this is just a non-commutative generalization of the theorem cohomology. It's not evident from what I said, but there is a totally obvious Hodge filtration on here. The point is you construct these both out of something called a mixed complex, and every mixed complex has a Hodge filtration on it. We used topological K-theory as a lattice inside of here. And one of the main reasons that we wanted to use K-theory instead of singular cohomology is when you work with non-commutative algebras, there's no such thing as singular cohomology. There's no space. How are you going to form simplices in something which doesn't exist? Fortunately, miraculously, topological K-theory also exists. So this is a fairly recent thing due to Blanc and Towen, and I guess a few others. And if this is like some, yeah, well, this recovers the commutative invariant if A is commutative, let's say. Okay. Also, over here, we have, I didn't talk about it, but as you change your Poisson structure, you're going to get a variation of those mixed Hodge structures, and it's going to have some canonical like Poisson version of the Gauss-Manning connection on it. Believe it or not, there is a non-commutative version of the Gauss-Manning connection due to Getzler. where he constructs this on any family, any formal family of algebras. Their periodic cyclic homology is going to have this connection on it. And there's a few different things you could say about the weight filtration, but let's not worry about it. Okay, so the point is, for almost all of these, there's some non-commutative thing, which you could also hope to construct a mixed Hodge structure on, like we did in the commutative case. And I'm not going to say really how we do this at all. I want to use my last minutes wisely. But let me just draw a picture for you. So the main idea is that, okay, here's this Q plane. There's the origin, and here's where Q is 1. Now, at Q equals 1, we've got this fiber. It's the commutative fiber, right? That's where it's an actual commutative torus. So here we have the theorem cohomology of A1, or HP of A1. This is the theorem cohomology of, I guess, C star squared in our case. Now, it has a filtration. One of these filtrations and so let's say this is the Hodge filtration. So what you can do is as you move around, you're going to, well, see how the filtration changes. So actually, I mean, on each one of these fibers, it has its own filtration. And then, you know, if for it to be a variation of Hodge structures, you're going to ask some compatibility with this filtration. But the important thing here that I want to say is that on this bundle, we have parallel transport. So if I've got any curve in the base going from, you know, Q equals 1 to this non-commutative point, then I'm able to parallel transport. Well, I can try to parallel transport sections from this fiber to this fiber. And what that's going to do is you can check it actually preserves the lattice. So if this is the lattice sitting inside of here, it's going to preserve the lattice. And since it preserves the lattice, what you can do is you can just parallel transport the weight filtration here, one over here. So the one sort of thing that we don't have completely intrinsically yet is what is the non-commutative version of the weight filtration. This, I don't really know what it should be. But in this case, when we have this variation, we can just take the weight filtration on the commutative fiber, which is defined geometrically, and we can just parallel transport it to get a filtration on any other fiber. And we do that. And then in this case, again, what I'm talking about right now is just for tori. In this case, you actually do get a variation of mixed Hodge structures. Let me just whip off a quick couple of facts about it. So this is going to look like the exterior, exterior algebra on the dual of the Lie algebra, where I view C star to the n as a Lie group. Okay, so this is like a calculation of the cohomology, or of HP. And yeah, I don't have time to say all that. Let me just set up the main point here. Okay, so the point is you get this mixed Hodge structure. And let me call this mixed Hodge structure K naught of AQ. Right, so for every Q here, this fiber is going to be this vector space endowed with a mixed Hodge structure. And from this, I'm going to get the same sort of exact sequence I did before. So I can look at K0 of AQ. This is Z. Or sorry, weight 0 of K0. This is going to map into weight 2 of here. And then when I take the associated graded, I'm going to now get z minus 1 again. And this is going to be spanned by 1 over 2 pi I E1 wedge E2 minus log of Q. Okay, where here E1, E2 is generators for the dual of the Lie algebra. Okay, so before we had this short exact sequence of mixed Hodge structures, here we also have short exact sequence. It's still well, I mean, this is like what we had before. It's going to determine one of these extension groups in this abelian category. And this is isomorphic to C star. And remember before what happened was here we had a lambda, and the parameter that it detected was e to the lambda. Okay, here we have log Q. And so you can maybe guess that this class is actually going to get sent to e to the log Q, which is just Q. So that means that we have some sort of Trelli theorem for non-commutative tori of this form. Okay, it's their mixed Hodge structure determines the torus or the non-commutative torus algebra up to isomorphism. Okay, the last thing I'm going to say is relating this back to deformation quantization. So I started with this Poisson variety, and I'm going to take its mixed Hodge structure. I just had K0. When I calculated this map, it basically sent this data, well, x sigma basically went to e to the lambda, where remember, this was lambda xy, del x wedge del y. Okay, now we know that when you do deformation quantization of this Poisson structure, we said this at the very beginning, that you're going to get a non-commutative torus algebra. The thing is, it's formal, so it's going to be like a q, but maybe q of h bar. We suspect q of h bar is e to the lambda. We don't know how to prove it, right? That's what we want to try to prove. Right, so remember this just says that xy is q of h bar, yx. And we just calculated for non-commutative tori, in particular, this algebra works. When you associate to them their mixed Hodge structure, so K0 of AQ of H bar, there's a Trelli theorem. So here you get Q of H bar. Sorry. Yeah, Q of H bar. Right? Okay. Now, the crazy thing, and the part that's actually extremely hard in this whole story, and which I basically contributed none to, but it's due to people like Thomas Willwacher, Alberto Cattaneo, Giovanni Felder, all these people who sort of worked on formality theorems and stuff like this, is that this induces an isomorphism of mixed Hodge structures. So this is going to be isomorphic to this Hodge structure on 8Q. Okay? We don't know what Q or Q of H bar, if you want. We don't know what Q of H bar is. It doesn't matter. These are isomorphic mixed Hodge structures. And the key thing is that since these were just coming naturally from like things in the weight filtration of these two things, since they're isomorphic mixed Hodge structures, these numbers have to actually be equal to one another. Okay. Now there's an H bar, here there's not an H bar. Okay, I can make things formal if I want. I could like complete at the origin, but this